Okay, so today we have lesson 10, conducting a simulation to estimate the probability of an event. This is very similar to a lot of the previous lessons we've done. Today it's just asking you to conduct a simulation. So to start out, it says, in previous lessons you estimated probabilities of events by collecting data empirically or by establishing a theoretical probability model. There are real problems for which these methods may be difficult or not practical to use. Simulation is a procedure that will allow you to answer questions about real problems by running experiments that closely resemble the situation. That's what they mean when they're talking about simulations. It means you're just like running experiments, whether it be rolling the dice, flipping a coin, pulling a card. You're just running a simulation or an experiment to check probability. It is often important to know the probabilities of real-life events the probabilities of real-life events that may not have known theoretical probabilities. Scientists, engineers, and mathematicians design simulations to answer questions that involve topics such as diseases, water flow, climate changes, or functions of an engine. Results from the simulations are used to estimate probabilities. That is important. That help researchers understand problems and provide possible solutions. So that paragraph is just saying that simulations can be used to estimate probabilities. However, we don't often know the probabilities of real-life events, especially stuff that is happening now, kind of like coronavirus, which is new and we're still studying. There's a lot of things we don't know about it, so simulations and real-life data can help us learn more about things that we don't know. Okay, so this is example 1. It's about families. This should look very familiar. We did a lot with this example in lesson 7. So example 1 says, how likely is it with a family that has 3 children, has all girls or all boys? So let's assume a child is equally likely to be a boy or girl. That means it's a 50-50 odds. So you can simulate having a child by tossing a coin. And if you get heads, we can say it's a boy. And if you get tails, you can say it's a girl, which is what that paragraph is saying. So if we go to exercise 1, it says, suppose that family has 3 children. To simulate the genders of the 3 children, the coin or a number cube or a card can be used 3 times, once for each child. For example, 3 tosses of the coin that results in heads, heads, tails represents a family with 2 boys and 1 girl. Note that heads, tails, tails, heads, tails, heads, and tails, heads, heads also represent 2 boys and 1 girl. This is just saying when you either roll the dice or when you flip the coin 3 times, it's going to give you the outcome for a group of 3 children. Suppose that when a prime number is rolled on the number cube, it simulates a boy birth. And a non-prime number simulates a girl birth. So we have prime is going to be for a girl and not prime is going to be for a boy. Oh, I think I flipped that around. I flipped that around. So prime is going to be for a boy and non-prime is going to be for a girl. Using the number cube, list the outcomes that would simulate a boy birth and those that would simulate a girl birth. Are they equally likely? So if we're talking about a number cube, a cube has 6 sides. So we would have numbers 1, 2, 3, 4, 5, and 6. So a prime number is a number that is greater than 1, that is only divisible by itself and 1. That means when you can't multiply 2 numbers together to make that number. So our prime numbers here are going to be 2, 3, and 5 because no 2 numbers when you multiply each other equal 2, 3, or 5. It won't be 4 because you can do 4 times 1 to get 4, or you can do you could do 2 times 2 to get 4. So this is why it's not prime, because you can do 2 times 2. With 6, you could do 6 times 1, or you could do 2 times 3. So this one is not prime either. So our only prime ones are 2, 3, and 5. 1 is not prime because the definition is that it's a number greater than 1. So if we have our 6-sided die and there's 3 prime numbers and 3 non-prime numbers, that means that it is equally likely. So are the boy and girl outcomes equally likely? Yes. So for number 2, it says, suppose that 1 card is drawn from a regular deck of cards. A red card simulates a boy birth and a black card simulates a girl birth. Describe how the family of 3 children can be simulated. So this is just asking you to describe how you can use a deck of cards, just like we use the dice where you roll the dice. How could we use a deck of cards? So what we can just do is we can shuffle, then pull one card, and then the important thing here is we have to replace it. So with replacement, and then repeat. It is important that we have to, after we pull one card, we have to put that card back in the deck, because if you pull a card, it's a black card, it's a girl, and then you put it to the side, now there's one less card, like one less opportunity for a girl to be pulled. So technically you're changing the probability. The probability is the same every time. So you would have to shuffle it, pull one, look at it, then put it back in and shuffle it again every single time. So it's important right here with replacement. You have to replace the cards when you're using a deck of cards. So for example 2, we're still talking about our family. It says the simulation provides an estimate for the probability that a family of 3 children would have 3 boys or 3 girls. So all boys or all girls, by performing 3 tosses of a fair coin many times. Each sequence of 3 tosses is called a trial. If a trial results in either heads, 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 or tails, 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 then the trial represents all boys or all girls, which is what we're interested in. That would be called a success. So our success is going to be all boys or all girls, because that's what we're looking at for this example. If a trial results in any other order of heads and tails, then it is a failure. To estimate the probability that a family has either 3 boys or 3 girls based on the simulation is the number of successes divided by the number of trials. So we have success over total is the estimated probability. Suppose 100 trials are performed, and in those 100 trials, 28 resulted in either heads, 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 or tails, tails, tails. Then the estimated probability of the family of 3 children has either all boys or all girls would be 28 over 100. This 28 over 100 is because it was 28 successes over 100 total trials. And that would be equal to 0.28 when you divide that out. So for number 3, it says find an estimate of the probability that a family with 3 children will have exactly 1 girl using the following outcomes of 50 trials of tossing a fair coin 3 times per trial. Use H to represent a boy birth and T to represent a girl birth. So in the first example, a success was considered all heads or all tails because they were looking for all boys or all girls. In this example, our success, because we're looking for exactly 1 girl, would be either, which one is girls? Tails is girls, so it would be 1 T. So we could have T, H, 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 T, H, or H, H, T. I think that's it, because all of these have 1 T, so that's 1 girl. So this is what we're looking for in our data set. So you can take a quick pause of this video, see if you can find all of these and count up how many there are. Okay, so I have gone through and circled all of the ones with only 1 T. So when we count them up, there are 16 successes. That's 1 T. Over, we know it's 50 trials, 50 total. And then when you put that in your calculator, 16 divided by 50, you get 0.32, or 32%. So moving on to this next example, number 4, perform a simulation of 50 trials by rolling a fair number cube in order to find an estimate of the probability that a family with 3 children will have exactly 1 girl. So specify what outcomes of 1 roll of a fair number cube will represent a boy and what will represent a girl. So you can do this a bunch of different ways. You can say my even numbers will be boys and my odds will be girls, or vice versa. You can do what we just did and you could say prime numbers will be boys and then non-prime will be girls. You can do numbers 1 through 3 equals a girl, and numbers 4 through 6 equals a boy, as long as you're making sure it's even. So each of these, there's 3 even numbers, 3 odds, 3 primes, 3 nons, 1, 2, 3, 4, 5, 6. As long as you have even outcomes, you can do it however you want. So I went ahead and did this earlier. However, instead of doing 50 trials, I only did 20. The reason I did that was because it takes a very long time to do this. But what I want to talk about, why it is important to note that I only did 20, is because as we learned from lesson 7, the more trials you do, the more accurate it is. So if I did 20 trials instead of 50, what does that mean for my data? Does it make it more closer to being more correct, or closer to maybe being off a little bit? Like we said, the more you do, the more accurate it gets. So my trials might not be as accurate because I did less than 50. It is very important to note that. So we're going to go ahead and look at the data that I collected. And so it says, list the results of your 50 trials. That's this picture that I have right here. And so now it says calculate, oh, I'm sorry. Also, what I decided to do was I said that, I did the first example. I said that even is going to be a girl, and then odd is going to be a boy, is what I did when I did my trials. So that means an even would be a 2, 4, or a 6, which would be a girl, and then an odd would be a 1, a 3, or a 5. So we're calculating the estimated probability of a family with 3 children having exactly 1 girl. Okay, so now we're going to look through and see which ones produce the outcome of just 1 girl, which means just 1 even number. So right here, 5, 4, 1, and 2, 5, 3, 1, 4, 3, 5, 2, 1, 6, 1, 3, 1, 3, 2, 5, 1, 2, 3, 3, 2, 1, 2, 5, 3, 3, 4, and then 3, 6, 1, and 6, 5, 5. So these are all my ones with just 1 even number. So if we count these up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I had 12 successes over 20 total trials. So if I do 12 divided by 20, I get 0.6 or 60%. So in the trials that I did, I found it was a 60% chance of having just 1 girl. Now it says calculate the theoretical probability that a family with 3 children will have exactly 1 girl. So I'm going to write up here my experimental probability was 0.6. So let's see what the theoretical probability is and see how it compares to what we found with our trial. It says, list all the possible outcomes for a family with 3 children. For example, one possible outcome is BBB. All 3 children are boys. We already did this in lesson 7, so I put our tree diagram that we did right here. So the possibilities that we can have with 3 children is we can have girl, 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 boy, girl, and girl, girl, boy, and girl, boy, boy for girls first, and then we can have boy, 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 girl, boy, boy, girl, girl, and boy, boy, girl. So there's 8 total outcomes. These are the 8 that we have. So assume that having a boy and having a girl are equally likely. Calculate the theoretical probability that a family with 3 children will be having exactly 1 girl. So we've already calculated the theoretical probability of all of these as 0.125 in our lesson 7. But if we forgot about that, we know that any of these is technically equally likely. So we can do, for our 3 children, 1, 2, 3, probability of having like boy, girl, boy would be 0.5 times 0.5 times 0.5, since all of our probabilities are 50%. When you multiply that out, you get 0.125. So maybe you remembered it from before, or if you didn't, you can just very quickly, you know that every single one of these probabilities is 0.5. So if you do 0.5 times 0.5 times 0.5, you get 0.125. So calculate the theoretical probability that a family with 3 children will have exactly 1 girl. So now we have to look at all of our possible outcomes and see how many have exactly 1 girl. So right here, girl, boy, that's 1 girl, and then boy, boy is 1 girl, and boy, girl is 1 girl. So now we know that these are all 0.125, and we are going to add up 0.125 3 times because it occurs 3 times. So the probability of having exactly 1 girl is just adding these up. This is very similar to what we did in lesson 7. So when you add these up, you'll find that it is equal to 0.375 or 37.5%. Now that says compare it to the estimated probabilities found in A and B. Our estimated probability that we found was 0.6. That's our estimated. And then our theoretical that we found was 0.375. You should notice that these look very different. And it's good that we have already thought that we might get a different result, because I did only 20 trials when I did this, so I should expect to get a weird result. I didn't do enough trials to get close enough to 0.375. So if I were to do more trials, I should expect to get way closer to 0.375 or 0.4. So does it make sense that we have differing answers? Yes, it does, because we did less trials than they asked us to. If we did more trials, we should hopefully get somewhere closer to 0.375. This is our last example. It says, suppose that on average, a basketball player makes about 3 out of every 4 foul shots. So she has a 75% chance of making each of the foul shots she takes. Since a coin toss produces equally likely outcomes, we can't use a coin toss. So we could use a coin toss for something that's 50-50, but this is not 50-50, it's only 75%. So instead, we're going to use a number cube that could be used by specifying that the numbers 1, 2, or 3 is a hit. So 1, 2, or 3 is good. And then 4 is a miss. And then if we get a 5 or a 6, we're just going to roll again. You're ignoring 5 or 6. So if you're rolling, you get a 5 or 6, roll again. Based on the following 50 trials of rolling a fair number cube, find an estimated probability that she makes 5 or 6 of the foul shots she takes. So when I look at this list of numbers, I see that they list 6 each time. So what's the probability that she makes 5 or 6? So that means that she's allowed to miss 1. So we have to go through and find all of the trials and where there's only 1 4, 1 or less. Because if there's no 4s, that means she got all of the 6. So anyone that has more than 1 4 is disqualified. So like this one right here has 2 4s, so that means it's not a success. Our success, I'll define it, our success is going to be 1 or less 4s. So if we look, this one has 1 4, 1 4. You can pause and go through these yourself. So I went through and circled all of these, and then when you count them up, you should have found that 27 out of the total 50 had 1 or less 4s. So we said our success is 1 or less 4s. 27 had 1 or less 4s. So 27 over 50 is equal to 0.54 or 54%. And this was our last example. Comment if you have any questions. Hopefully this is a good review and you can practice. If you have more time, you can go back and add another 30 trials to our past example and see if you get to a closer probability than I did, and then you can see how much it matters how many trials you do. But that's all. Have a great rest of your day.